Similar figure or similarity. Okay. So, previously we talked about dilation, and the topic of dilation actually is tied closely to the concept of similar figures. Now, some objects are similar, some shapes are similar automatically. For example, if I ask you, if I make this statement, all squares are similar. Do they look alike? Do all square look like square? The answer is yes. Okay, any two squares are similar. Now, if I make this statement, all squares are congruent. Would that be true always? Would that be true in some cases or sometimes? Or it's never true? The answer is, while some squares are congruent, not all squares are congruent. So the statement about the congruence of squares is just sometimes true. The statements regarding similarity of squares is always true. So basic concept about similar figure, okay, we know that similar figures have the same shape. All squares are squares, but not necessarily the same size. All right, now some other figures like equilateral triangles, they are all similar but not necessarily congruent. We'll talk about circles, believe it or not. Now, let's get down the main concepts about similar figures or similarity that we will talk about in this portion of your work this week. Now, similarity or similarity transformation. We're going to be using other transformations plus dilation to show that two figures are similar. Blah blah blah. Okay, let's get down to word. Okay, it's staring right at you. It's gonna be, okay, in words, a similarity transformation. Okay, note that down and I will underline it for you. A similarity transformation is a composition of one or more rigid motion and a dilation. So a combination or a composition, we'll talk about composed transformations, of one or more rigid motions, meaning translation, reflection, rotation, and a dilation is what we refer to as similarity transformation, meaning they will result in similar figures. Conversely, we can show that two figures are similar by showing that one figure maps onto another via a series of rigid motions combined with a dilation. Dilation always produces similar figure. Bullet point number 2. Two figures are similar if there is a similarity transformation that maps one to another. What I just said. All circles are similar to each other. Duh! All circles are similar to each other. Of course, believe it or not, you will be asked to prove that all circles are similar, while it is obvious. Now, let's look at these diagrams right here. We have triangle ABC is similar to triangle XYZ because, as the diagram is showing us, there is, okay, triangle ABC can undergo a series of transformation. Okay, the first being a rotation. Okay, it's being rotated like that. Okay, and then a dilation. So rotation plus dilation. Okay, rotated some angle and dilated from some center. Okay, from a center, you will be able to map triangle ABC onto triangle XYZ. Look at this. The triangle ABC is similar to triangle XYZ because, okay, the transformation that can happen are, number one, rotation, rotate. Okay, rotation, and then okay, we have the dilation, which is the key ingredient. Okay, and then dilation maps triangle ABC onto triangle XYZ. Let's look at the circle. Believe it or not, you should be able to prove that all circles are similar. Now, guess what? What transformations do we need to use in order to show that circle P is similar to circle Q? All right, now let's see. Let's see, because this is so hard. It's gonna be okay. Let me diagram it for you. Okay, slide point P to Q. Boop boop. All right, it's gonna be point P will side Q. That's what is that? What is that? It's gonna be what? A translation. Translation. Okay, so the first step is translation. So you're gonna have circle P right here. Toot toot. Okay, I did my best. Okay, don't judge me. It's gonna be now circle P and circle Q has their own radii. Okay, radiuses. Now this is the radius. Let's say this is the radius of circle P. That radius right here. Okay, using point P as the center, you can multiply the radius by some number. Since point P is smaller than, circle P is smaller than circle Q, you have to enlarge it. So you have to multiply by some number greater than 1 in order to map all the points in circle P onto all the points in circle Q. And when we are multiplying lengths by the same magnitude or number, okay, that's a property belonging to a dilation. Okay, so we have a dilation. So a series of, okay, a combination of translation and dilation maps circle P to circle Q, and therefore they are similar, or it's kind of obvious. Now, question. Okay, do we need rotation? Okay, as part of the series of transformation to prove that two circles are similar. Well, if you rotate a circle, it still looks like a circle. So rotation does not help in any way. So rotation is not necessary. If you flip a circle, okay, it still looks like a circle because all points on the circle are of the same distance from its center. So reflection, neither. So the only translations necessary to prove the two circles are similar is translation and dilation. Moving on. Okay, moving on. Now you will be in this portion of the lesson. You will be reading about composition of transformation. Composition is just what we did. We combine different kinds of transformation into a sequence of transformations. So that means composing. So you're performing one transformation, producing one partial image, and then you will perform another transformation on the image to produce the third image. That means that's what we mean by, say, composition of transformation. Now let's look at some compositions. Most importantly, the composition of transformations that you will use to prove that two figures are similar. Remember, in a composition of transformation, when we actually perform the composed transformation, we always do the second mentioned transformation first, kind of backwards. All right, I will show you what it means. Okay, one kind of composed transformation is the composition of dilation and translation. How do we write it? Okay, now let's look at this one here. Okay, you can read this as this: the image of triangle ABC under the dilation with a scale factor of 3, that is this part right here, composed with the translation of 2 right and 1 down. That is this part right here. Okay, so we have the dilation part and the translation part. Now, when we actually perform this composed transformation, guess what we're gonna do first? We will do the translation first, and then after we have translated, we will do the rotation, and that's gonna be the same pattern in any transformation, any composed transformation. Meaning, in this transformation, you will apply the dilation with a scale factor of 3 to the image after doing the translation of 2 right, 1 down. Blah, blah, blah. All right, next, composition of dilation and reflection. Okay, so we have, how do we read this again? The image of triangle ABC under the dilation of with scale factor of 3 composed with the reflection over x equals 1. So we have, this is the dilation. Okay, pop quiz again. What is the center of this dilation? Okay, if you said the origin, you remembered right. All right, so you have, since the center is not indicated, the center is the origin. And then the reflection part is right here. In a reflection, the element of reflection is a line of reflection. Here, we are reflecting over the line x equals 1. It is a vertical line intersecting the x-axis at 1. That's not the lesson today. So, reading. All right, the image of triangle ABC under the dilation with a scale factor of 3 composed with the reflection over the line x equals 1. Take note, sometimes the line is named by a letter. For example, we can say that given M, line M, is the line is defined by x equals 1. So you can rewrite your composed transformation as d subscript 3 composed with r. Instead of writing the equation of the line, you can write the name. The name is m. Okay, that means the same thing. Moving on. Composition of dilation and rotation. Okay, just read this. Okay, I'll read it and then you read how it read. Ooh, 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 ooh. Okay, that's cool, right? I'll read it. I'll read the notation and then you will read how it's read. It's gonna be the image of triangle ABC under the dilation with scale factor of 3 composed with a rotation, small letter r, because the capital letter R is for reflection. Okay, rotation of 90 degrees counterclockwise with the center at 0, 0. Now remember here, the center here is the center of reflection, not the center of dilation. So that's how it's read. And guess what? The pattern is you do the second mentioned transformation first. So here we're gonna be doing the rotation of 90 degrees first, and then you will do the dilation of 3 on the image after doing that. All right, so these are hopefully this helps you, okay, not get shocked when you read and when you see this notation in the upcoming example. So again, proving to figure similar means showing that there is a series of transformation, rigid transformation, combined with a dilation that maps a figure onto another figure.